So yeah, there might be a couple more people coming in a minute, but I just wanted to start today and introduce myself, Tom Meltzer, Senior RSC in the ICCS, and I'm joined today by a fellow Senior RSC and fellow team co-lead, Marion, Weinzierl. We're going to do a bit of high-performance profiling today. So we're going to cover a range of different topics. We're going to start by looking at sort of compiled languages, how you can profile them using an open source profiler. We're also going to show some, Marion's going to take over and do a demonstration of profiling, but in Python. And then we're going to sort of round off the session by looking at how to kind of look for memory bugs or look at tools that kind of investigate memory. And that will apply both to well, mainly to compiled languages, but also I've been told Python as well. But your mileage may vary. So that I'm kind of planning the first hour and first sort of hour and a bit doing theory, and we're hoping to give you sort of 50 minutes so that you can take any one of the concepts that you're learning today and put it into practice with your own code. If you don't have, or you think, your code doesn't run on your laptop or it's too big, there are going to be some test cases in the GitHub repository that you can download. So with that in mind, I'm just thinking ahead, because the internet's not super great, if anyone wants to go and start cloning the repo, it's very small, this one, it's not big, but you can go to our Cambridge ICCS GitHub, and we're in the profiling workshop repository. So you can clone that. It's got some example demos, memory, Python, Scorpy. If anyone wants to do, in the practical session, they want to kind of profile their code, and it's a compiled code, I recommend downloading Scorpy whilst you wait. Let me do Scorpy. And I'll just, so always like a million ways to get it. Actually, no, this is the best way to get it. So go to, I just Googled Scorpy download. You can go to their website and you can find the releases. And then you can get a zip or a tarball of the latest release, which is 8.4. So if you want to start that off now, in an hour's time, it should have downloaded. It's really not that big, but it's definitely going to push the Wi-Fi if everyone does it at the same time. So without further ado, let's get started on some theory that will explain what profiling even is. So why do we care? Well, there's this famous quote, and every profiling workshop's going to have it, but essentially the bottom line is premature optimization is the root of all evil. And so a lot of the time, as programmers, we're sometimes thinking like, oh, what's the best way I can do this? What's the best way I can do that? And the answer is get it done first, get it working, make sure it's correct, then profile it. Okay, so don't try and guess at the start, oh, but if I use a structured arrays or an array of structs or this or that, get it working and then you can profile it. And that's going to be the kind of summary of today. Rather sadly for me, as someone who likes profiling and high-performance computation, there was a survey recently, this is the Rust developer survey, and they asked their community in 2022 and 2023, which profiler do you use to profile your code? And a shockingly large number, 82%, 73%, said, what's a profiler? I don't use profiling tools. And then, less so said, things like perf, call grind, cache grind, or maybe their IDE, okay? So really, yeah, that's, after today, we want to kind of take that 82% down and boost the number of people that see the benefit of profilers. So my motivation for getting in, specifically to Scorpy, which I'll show you in a minute, which is a profiler, my motivation for finding profilers was, I don't know, about a year ago, I was assigned to a project to work on weather code that was the German equivalent of the Met Office, and the code's called Icon, and there was a submodule called MSG WAM 3D. They're looking at kind of modeling gravity waves. Some people may be in this room from that project and from DataWave. And Icon's got 2 million lines of code and spread across over 2,500 different source files, including C, Fortran, C++, and it's mostly a Fortran code though. And they said, look, oh, it's not performing how we expect. Okay, where do you start looking, right? It's no longer possible to guess where performance bottlenecks are going to occur, and even educated guesses are likely to be wrong. Codes are so complicated, the hardware is so complicated, it's not necessarily obvious where your bottleneck is. You know, maybe it's in communications, maybe it's in data, maybe it's the algorithm, and so we really need a scientific approach. So we're scientists after all, and the best way is, we don't just want to guess where the problem is, we want to be able to measure it, okay? And profilers are going to be that tool, that kind of scientific instrument that we're going to use to investigate our code and start to think, where are the problems lying in it? So for profiling, you could think there's a number of different ways to kind of get this information, like find out how long is my code taking, where are the bottlenecks. You could go into your code, your source code, and litter it with printf statements manually and time regions of interest. And okay, that's one approach, but you have to manually do that, and it's going to be very time consuming. You could use things like logging. Similarly, you can have like little timestamps and see where you get to different bits of your code, but then processing that's going to be quite a pain. Profiling, which is going to be the subject of today, there's couples of different methods. We're going to talk about sampling, instrumentation, and I'm going to tell you in a couple of slides exactly what sampling and instrumentation mean. But I'm hoping that today we're going to see the benefits of, say, profiling and tracing. We're not going to cover tracing today because it's a little bit more advanced and it's a lot more in depth, but it's an equally valid tool. I've also got some little honourable mentions down here. So there's an article Chris shared with me recently called Control-C debugging. For any code that takes a long time to run, chances are if you just Control-C, you're going to hit it at the point it's taking too long. It's a sort of a sampling method that we'll come on to later. And then there's something called OpenTelemetry, which isn't ready yet, but they're aiming for a version 1 release where they'll have kind of an option for profiling. It's completely different to the stuff I'll be presenting today. But if anyone's interested, we'll send you these slides and you can click on the links, find out more about them. So my job today is to convince you the first two options are bad and the second two options are good, and that they'll be very useful to you in your careers. So I wanted to explain, well, what are the words I've just been saying? So profiling is this idea that we're going to run our code and be able to kind of study it and find out how long things are taking, maybe which functions are getting called the most. And there's different ways to do this. So the three main approaches can be grouped into different categories: sampling, instrumentation, and tracing. I've got cartoon diagrams on the left-hand side there, and I just want to explain a bit about the cartoon diagrams, and then I'll explain what the different methods are. So each one has two processes running, okay, in this cartoon picture. There's process 0 and process 1. These colored blocks represent function calls, okay? So you could have an initialization function, might be this blue one, or it could be an MPI function that spawns then some work that goes to these two processes. This orange one could be like a heavy compute-intensive function that takes a long time. And we've got this idea that along the x-axis, we've got this concept of time going forward, okay? And then this yellow one is like a really quick, short function, and that could be something like a print statement. So I print, currently on iteration 10, right? That's going to be very quick, and it's going to go in a flash. So we've got this idea that we've got these function calls, they're different functions, and they have some kind of temporal information. So with sampling, what happens is at regular time intervals that you can choose, it's going to interrupt the code. So the code's running, and then it's going to stop, and it's going to say, please, give me a stack trace, a back trace. What function are you currently in? What line number is it on? And it will send that information to the profiler and collect it, like aggregate statistics. What can happen is we can see that we stop at regular time intervals, and we can see that we've accidentally missed this yellow function. So we're going to come on to this a bit later. But if you stop at regular intervals, there's a chance that if a function's quick, you've missed it, okay? And so the two ways to find that are you're either going to have to increase your sample rate, make it quicker, Or you maybe perhaps call this function more times. Maybe you call it like 1,000 times and do a study on it. But sampling innately relies on statistics. As the name implies, you're sampling from your program sort of the profiling information. Instrumentation's different. So instrumentation typically is done with source code level instrumentation. So instrumentation is where you add hooks to your functions. So every function in your code gets a hook at the start and at the end. And that hook links to the profiler to say, oh, I've just entered function A. Oh, I've just left function A. Now I'm going to function B, and now I've left function B. And it can give you the temporal information and some other statistics like how many times that function's been called. And what we can see is, contrary to the sampling case, these arrows are exactly lined up with the function start and end. So it doesn't matter how quick your function is. If you've got a function C which is very quick, you're always going to capture it. But as I'll discuss later, that comes with a penalty. Instrumentation adds an overhead to your code because each function has a hook. So if you have loads of these repeating functions that get called, say, 1 billion times or 1 million times, your profiling is going to be, your results are going to be skewed by the cost of adding this, the instrumentation. So it's something to bear in mind, and we'll talk about strategies for that a bit later. Tracing is sort of like the I don't know, like the ultimate pairing of everything. You get a lot more information. So you get this, it's like instrumentation. I mean, you can also use sampling, but in this case it's showing instrumentation with tracing. You have the start of the function and the end of the function, but you also get this kind of idea of causality. You can see, function A called function B, or this function then led to this function. And tracing can be really good at looking at things like race conditions. But it can also just be really good, especially if you've got like distributed codes. You can see, which data was sent from which process to which process, and you can kind of track this like spatio-temporal flow through your code that you don't get with instrumentation and you don't get with sampling. Sampling and instrumentation, I'll sometimes refer to this as like a flat profile, because there's no temporal element. Like that gets lost. What you get is at the end of your code run, you get aggregate statistics. You get the sum of like how many times a function was called. You get how long it took that function to take. Maybe the mean of that function, the min, the max. But you don't know that function A was called at 10 past 2 and function B was called at 10 past 3. Whereas with tracing, you get a timestamp of events. You can see the sequence, but that comes with some costs I'll discuss. So I just want to do a high-level overview of the pros and the cons and why you might use them. Sampling, typically low overhead. Well, it's low overhead. You typically don't need to recompile your code. So for like things like C, C++, Fortran, that can be beneficial. High volume of quick functions is not an issue. So I mentioned in instrumentation, there's an overhead. Every function gets instrumented. So for sampling, it can be good for cases where you have like billions of repeating quick functions. Cons are that it can miss a quick function if it's only called once, as shown in the example, and it's subject to sampling bias. So if your code runs too quickly, say you've only run your code for 10 seconds, your sampling is going to be terrible, your statistics are going to be terrible. You shouldn't do any performance analysis on, like any kind of scientific experiment. You need statistics if you're going to use the results and infer from them. Yes, please. Well, just to be clear, it's not necessarily that you're looking for a bug. So when I think about bugs, I think about debugging programs, and I might use tools like GDB or something like that to spot an error. You can spot maybe conceptual errors or bad design practice, but you're not necessarily, it's not to say that you can't find bugs with profiling, but it's not maybe the main goal. You're mostly trying to tune performance. And so if you have a quick function, maybe like if that's called a lot, many times, you might want to accurately know, well, how much of my code is spent doing this function. It depends what you're investigating, but chances are, for the most case, if you're sampling, if something's quick and you miss it, you probably don't care about it. because that's why you missed it. It's the times that you're spent waiting for things, that's probably where you want to find out what's happening. But there can be different use cases, different reasons you might want to know about the quick function. But typically I find instrumentation gives kind of more, I find the information slightly better to digest and more accurate, but it comes with the overhead, so sometimes sampling is then better, and then you just be aware that you can miss functions if they're quick. But it's not normally a problem. So if we go to instrumentation, it's not subject to sample bias because you get what you get, right? You get exactly what happened. Every function call, you can see it. Quick functions are always caught, but it does come with a time overhead, and you do typically need to recompile. There are dynamic instrumentation codes, but typically I use source level instrumentation, and that's what I'm going to do in the demo, and I'll explain a bit about what that is when we get there. Tracing. You preserve spatiotemporal relationships. I mentioned this idea that you can see a timeline of your functions. You can see when they were called, and you can see arrows even to say like MPI data was sent from rank 0 to rank 5, right? So you get this, this notion of causality that you can follow through your program. And flat profiles, the ones I mentioned earlier, like the sampling and the instrumentation, you can always generate them from a trace, because you can just see it as like aggregating the statistics. You're effectively like collapsing that time dimension, and you're getting aggregate statistics. So you can always recover the profile from a trace. But here comes the cost. Traces get very large very quickly for, especially for climate codes or any high performance code that runs on a large system. So there's a higher overhead of memory and time, so the time it takes to collect the data and also the memory that it needs to buffer that data. Just as an example, for the icon code I was looking at, I looked at using tracing, and I found out that to run it for like less than a minute on a single process, it generated 2 gigabytes of data. And if I was going to run that for production level, where we were using 2,000 processes, we'd be looking at terabytes of data per minute, and it was just not feasible. And I needed like 20 minutes of run to do something meaningful, so I couldn't use tracing. And then typically you need to recompile and tune. So I've mentioned instrumentation, you need to recompile, fine. Tuning, I'm not going to cover it today because we're not going to look at tracing, but typically you want to cut out certain functions from the trace because they'll just give you loads of really quick hot functions that run quickly. You're going to get a lot of trace information from them, but it's not something that you really want to optimize. And so you typically go through this process of you tune it, you try and get rid of function calls you don't care about, you see how much data it's going to produce, you tune it, you recompile, and so it can just be a bit of a pain or a dark art. Yes. Yeah, so thank you. It's a good question. The question was, sort of to paraphrase, when is tracing useful? And essentially the answer is, I think for things like race conditions, or you might find when you look at the kind of spatiotemporal element, you might find that there are load imbalances, and so you might see that maybe one process is doing all this work and and maybe it's overloading some other process, sending all this data. You can track which data goes where, and maybe you're not using NUMA nodes effectively. Maybe there's like bad data locality. So there's like a lot more information that you get from that might be useful. But normally I think of things like race conditions, stuff like that can be really handy to use tracing for. Yeah, but equally you can get a lot from instrumentation. I mean, I use that for the icon code, and you can get a lot of information. It's just, I think you lose if the temporal component, i.e. like the timeline of events, is important, you need tracing. Yeah, thank you. So today we're going to cover Scorpy. It's just one tool, one open source and free software. There are a couple that I've used. There's another one called Tau, and I've got a link in the slides that you can have a look at. It's similar but different. It has different strengths and weaknesses. It's a really good tool, and there's some really good documentation. I've just picked one because we don't have enough time to do both. Technically, Scorpy is capable of sampling, instrumentation, and tracing. We're only going to cover instrumentation, and specifically I'm going to look at source instrumentation. So there are tools that can take a binary file and then modify the function calls and analyze that binary file, but I like to do source level instrumentation where you give the profiler, you say, here's the source code, instrument it at the source level, and then make me a binary. And it will do that by adding like kind of macros and if defs. You don't do that yourself. That's done by the compiler wrapper, and I'll show you that in a second. It has C, C++, and Fortran APIs. This was really crucial in me kind of switching to it, is that because it has an API, you can also do custom things in your code. So you don't have to, you can use completely vanilla profiler, but if you want to do something funky, you can sort of program the profiler as well, which can be really handy for certain use cases. It's production level, like I ran it on thousands of cores, but it scales up to tens of thousands of cores. It's designed with HPC in mind, and it adds minimal overheads in terms of memory and time. There is always an overhead, but they've just really worked hard to make that as small as possible. So how do you start using ScoreP in your project? If your project has a CMake build system, then these are the commands. I'm not expecting anyone to memorize this. I'm not going to test you on it. But you will perhaps get a chance if you want to run it on your own code, then I recommend you take a look at the slides. Essentially, the key bit I want you to focus on is these compilers. You get these, instead of using GCC, you have ScoreP-GCC. Instead of using G++, you have ScoreP-G++. These are called compiler wrapper scripts because they wrap typical GCC, G++, and they add the necessary libraries and the necessary functions to instrument your code. If you use something like make auto tools, then you can use this second approach instead. Yeah, but we're going to help. I'm going to mull around, and I've got helpers today. Marion's there, and maybe James, and anyone else who wants to volunteer helping. But we'll sort of mill around and help if you have issues compiling your code. So I now want to kind of show a live demo of. I'm going to take a small example code. We're going to run it, profile it, and I'm just going to explain what the profiler looks like and how we can use it to infer some information. When you get the slides, you can click this link and it will take you to our repository. For anyone that's already found the repository profiling workshop, we're going to be doing the ScoreP demo at the moment. So I'll make this bigger. I'm not expecting anyone to read this now, like word for word, but just to say that there is a README here, and it completely describes, how to install, how to build, example of running it, example of what the output looks like. This is all the stuff that I'm going to cover now, but if you go away and maybe some of it went too fast, you can go back and read this and play around with it in your own time. So without further ado, let's jump into a live demo. So I have cloned already the profiling workshop to my system, and I'm going to go into ScoreP demo. Now, importantly, I'm not going to show this step, but I've already installed ScoreP on my system. In the last hour, when you get a chance to do the practical, you can play around with it and try and do that yourselves. So I'm not going to show how to do that. So I have a code. It's called, yeah, sure. One second. Is this one? Got to wait a little while. Maybe this one. Yep, we're good? Is that readable? Yeah? So I'm going to open the code and just quickly describe it a little bit. So it's a Fortran code, and sorry for anyone who's not happy with Fortran, but I had to pick one language. We're going to initialize an integer, and that's going to set our problem size. So currently it's set to 2048, and then we're going to make some arrays that are n by n. We do some MPI initialization. Any MPI code is going to have this stuff. It's just boilerplate. And if we're on rank 1, so if process is equal to rank 1, we're going to generate some data. We're going to call a computationally intensive function, and then we're going to call a quick routine. I'll show you what those look like in a minute. And then we're going to do some sending of data. So if process is rank 1, we're going to send data to rank 0. And if our process is rank 0, we're going to receive that data from rank 1. So this will be important when we come to see the profile information. And then I said I'd show you the functions. So we have computational intensive is going to do a loop, and then it's going to do some mathematical arithmetic. This is just it's just made up to do something on the CPU. And then we've got a quick routine that prints something, and a nested quick routine that also prints something else. So that's kind of the layout of the code. It's just completely contrived, but to give an example of what a profile looks like, and then you can modify it, change it if you want to play around with it. So let's go, first of all, we want to sort of build this code. So I've got a make file that's included. It relies on you having OpenMPI installed already. There's instructions in the README how to install OpenMPI if you don't have it already. But I'm going to make all, which is going to build the classic binary, so not instrumented at all. But then I'm also going to use this scorp wrapper compiler, so scorp-MPIF90, and that is going to instrument the code. Okay? So let's make this. When I run make, we can see it built the code as normal. So it's built simple.exe, but it's also used this scorp compiler wrapper that's also building the code, and then I called it -inst. You can call it whatever you want, but the key here is it's got all those function hooks I told you about earlier. So if we run simple.exe, I need to MPI run, and I'm going to give it 2 ranks because I've sort of programmed this contrived example, and it's going to run on those ranks, do some fake computation, well, actual computation, but not of serious importance, and then it's going to print some quick stuff and finish. And if I do an ls, nothing new, nothing changed. Now, I've already built the instrumented version with the scorp wrapper. That's the key. So now if I run the instrumented code, simple.inst.exe, it's still going to look the same. It's going to run just like the normal binary, but when it's finished running, we're going to see some new stuff. Oh, I didn't run it with MPI. Should run it exactly the same, so ignore that for a second. I'm going to rerun it. Finish. It should take close to the same amount of time for a serious code. So, like, just to give you an understanding, for the weather model that I've instrumented and profiled, it was about 25% slower with the instrumentation in. So, for like a real code that was doing climate simulation. Now, if I do an ls, I'm going to have 2 because one of them failed because I didn't use MPI. But what you would have done if you'd done it properly, like the second time where I had MPI run, you've got this new folder called scorp and then a time date stamp. Okay, and in here, scorp, there are 3 files. There's a markdown file that just explains what the other 2 files are. There's a configuration file which I can open, scorp.config. This tells you all the environment variables, what they were when you ran the profiler. So it's just useful for bookkeeping if you forget. And then the important thing that we really, really want is that profile.cubex. So scorp comes with a program called cube. And cube is how it views the profiles that are generated by scorp. So we're going to do cube scorp and then the profile.cubex. And this will open our profiler, which is probably unreadable. Let me change the font size. Plugins, help. Where's my set font size? There we go. Maybe 18. Is that legible? Bigger? Happy? Everyone's happy. Brilliant. So there's some things I want to talk to you about this profiler. And kind of, the reason it's called cube is it has this kind of, based on this like the idea that the data is 3-dimensional. So you've got your metrics on the left-hand side. So I'll come back to the metrics in a second. In the middle, we've got our call tree. So these are the functions that have been called. Currently, it's all collapsed up into the top level. So this is just the binary we ran. I'm going to click expand all. here's all the functions that were called. So we had some MPI stuff. I had the quick computationally intensive routine. I had a quick one. I had a nested function, and then some other MPI stuff. So these are all the functions. So now I can look, I'm going to come back to the metrics. So currently I'm on metric, which is the number of occurrences, how many times this function was called. It's really not interesting for this code. What I'm more interested in is how long things took. So I can look at the time. Okay? And now I can see that bright red computationally intensive function is sticking out like a sore thumb. Now it's aptly named. This is where all of our computation's done. No real surprises there. One nice thing, if I collapse this again, collapse all, you can do expand largest. If you've got millions of functions, million function calls, whatever, this will jump to the one that takes the most amount of time, and that can be very useful. But a couple other things I want to show you before we move on. Now on the right hand side you can see the source view. So this will show me in the source code where these functions are, so I can remind myself, oh, what was the quick routine? Oh, I can see that. What was this one? And also I can see the nested quick routine. So that can be very handy, jumping around a large code base, just to remind yourself, oh, what's this function? Why does it take so long? Maybe it should take a long amount of time, you know? That's also fine. Something else I want to show you is we can have a look at the system view. Now, it's not going to be very interesting because this is my laptop, but you could imagine this for a very large system with multi-nodes. So I'm going to expand all. What this shows you is the first level is we ran it on this machine, which is a Linux machine. Then we see node Lenny. Now, Lenny is the name of my laptop because it's Lenovo and I'm not imaginative. But if I had many nodes, I ran it across a distributed system, I would have a drop-down for each system. On each node, I would then see the ranks. So I'd see each process individually, and you can also subdivide it and see threads and things like that. This code doesn't have threads though. And so what I want to show now is if I click on the left-hand side, the statistics will update automatically. And I want to go to this thing down here. This is bytes sent and bytes received, and this relates to the MPI communication calls. So I had some MPI in my source code. So what I can do is I can see bytes sent, right? And I can see MPI send, and I can see that it's red for rank 1. And if I go back to my source code, I'll have to make a new tab and make it big and open simple MPI 90. If I go back to my source code, you might remember that I said for rank 1, it's going to send data, and rank 0, process equals rank 0, that's going to receive the data. So now if I go back to the profiler, rank 1 did indeed send, 1.687 bytes times 10 to the 7, and fair enough, it was received on rank 0. So you can imagine this being a lot more complicated. Maybe you want to know where data is going to and from. Maybe you can see also some signs that there might be some imbalance, but just bear in mind this is not temporal, so it's aggregate statistics. So there's one more thing I want to show you before I wrap up on this side, and that's that we can also use hardware counters. So hardware counters hardware counters can be accessed by a variety of different tools. So there's something called PAPI, which provides an API to interface to them. And there's also Linux Perf, which is only on Linux, sorry, for Windows users. Or I don't know about Mac if it also works on there. But hardware counters can be things like they're kind of physically on the CPU, so on the host device, or you can get them on other devices as well. But typically we're talking about CPUs, and you can see things like how many cache misses were there, or how many clock cycles. You can get some really intricate information from the hardware counters that live on the CPU. And one of them that I think is very useful is this aforementioned cache misses. So typically, any code is going to have a cache miss. A cache miss is where you went to get some data from RAM. Well, the CPU requests some data. It looks in the cache. It doesn't find it. That generates a cache miss, and then it requests the data from the RAM. Okay, and then that data gets fetched from memory, goes into the cache, and then it can do some computation. You really want as few of those as possible. You'll always have some, but the less you have, the better it is. So I just want to show an example of how we can add that to the code, add that to the profile, sorry, just using an environment variable. So there's a run script that's included, I'm pretty sure I included it in the repo, but if not, I'll push it shortly, that demonstrates how to run the instrumented binary and collect perf hardware counters. You run this line 16, so that's export score p underscore metric underscore perf, cache misses u, okay? And then you run the code as we did before, so MPI run -n2, the name of the binary. So let's have a look at what this does. Before I do that though, I just need to comment that hardware counters are sometimes locked on different systems. You may need to speak to your HPC admins to enable performance counters. There's a quick way to check if they're disabled or not. Perf list, perf e, stat e. 1 second. I'll make this simple. I always forget the syntax, so stat e minus e. And then I think I said cache misses u. Oh, this always happens to me. Install, nothing like a live demo. For some reason, every time I update my laptop, this goes missing. I hope the internet works for me. Please. All right, okay, let's try that again. So I'm expecting this to fail, and I'll explain why in a second. So it can't find this. I'll just make sure I spelled it right, but it should fail anyway. And then paste. Yeah, okay. So this will fail because I've not enabled it on my system, and so to do that, I need to edit a file. Not Image Magic, this one, paranoid. This by default will be set to something like 4 on your system, but you can set it to 1, 0, 2, 3, depending on the security level. This is my laptop. I don't care, I'm going to set it to 0. There's no multi-user system. But that's why I'm saying that if you run it on HPC, it might be disabled. You typically need to get added to like a profiling group or something like that, run on an exclusive node, because there are security implications. So now that I've set that variable, I should be able to check per stack cache misses. I need to run a command. And you can see I've got, in 2 seconds, I've collected how many cache misses occurred on my operating, like this is operating system, everything. It just recorded everything. So going back to the code, if I count this, run, I'm going to export this metric. I'm just going to do an ls. I'm going to delete the old one so I don't get confused. And now I'm going to collect my profile again by just running the code, running the instrumented binary. But what I want to highlight is there's going to be now an extra option in our profile. So if I open the profile that's been generated, and then it's profile.cubex, I'm in a new thing. 1 second. Cube. So the reason that didn't work is I have score p, like a module loaded on this terminal and not the other one. Okay, so now the thing I wanted to show, if I move this over, is we have this extra line here, cache misses. Why can't I make this smaller? So I'm going to expand my tree, expand all. And I mentioned, like any code is going to have cache misses, and typically it's where you're reading data in. And so in this code, the largest number of cache misses are where we're doing the computation intensive stuff. And that can be understood because we have a large matrix that we're kind of timesing by itself, doing some operations on. It needs to load that matrix into the RAM. That's going to generate a lot of cache misses. But if they're not where you expect them to be, then you need to think, oh, maybe I need to optimize this. Maybe this should be changed. Maybe I need to change my data structure or my data access patterns. And that may reduce the cache misses for you. That's everything I've got time to show you now. We'll have a time for you to play around. You can follow the README and get this working on your own system. But I'd strongly encourage you to set it up for the code that you actually run. And hopefully I can show you that it's not too onerous to do that. So now, I'll leave some links in the slides, documentation. There's a really good tutorial at Oak Ridge National Lab. It's like 3 hours long, and it goes through this in way more detail. And then some extra information there. I'd now like to hand over to Marion, who's going to talk about the Python profiling.
Yep. So some of you might might be quite happy with what we have seen here. Now, some of you might think, okay, I feel I've been thrown a little bit in on the deep end. I am not interested actually in the fortran code on MPI, so I've got a serial Python code, and I just want to know what's actually the function that takes the most time, or where is the bottleneck in my code, where do I have to look if I want to optimize something. So we will talk a little bit about, okay, what tools are there to do that in Python. So there's a whole range of tools, and from the very basic ones like Timeit to a bit more sophisticated ones. So we will look at two in particular. We will look at cProfile and at the line profiler. There is Profile itself, which is very similar to cProfile and maybe a bit more adaptable, but adds a little more overhead to your program if you're running it. And one thing that I would just mention here before I show you how to use the two tools we're looking at today is PyTest profiling. That is a plugin for PyTest based on cProfile, and you basically decorate your functions and then can run this basically as part of your tests suite, and then you can create really nice graphs and call graphs and so, and see directly where your time is spent. So much for what there is out there on this slide. Oh, this slide has changed. So we have two examples, and they are both on the GitHub repo. So you can see the link down here again where the repo is. And I'm just switching over here to the go into the Python. So this is the repository in case you've cloned it, and you see here we've got two little examples here, the line profile and the cProfile one. Let's look into the cProfile code. So this is a very, very simple code. So what I need here, this is a fancy mouse. How do I use that? I click on something. So we have just this simple import of the cProfile library, and then these two are just so that we can look at what's coming out. I'm not using that mouse. So what this does, it's got two functions, and both are just running through some numbers and printing them out. And then here on the bottom, I've got something actually to do with the cProfile. So just as a side note, you can also run this from your terminal, but just for demonstrating purposes, I'm showing you here how you're putting it in your code itself. So you run your function here, and you create some statistics, and then you use the pstats package to use these statistics to tell you something about your program. You can sort the output in various ways. You can either look at the time itself in a function, or the cumulative time of the function and the function it calls. This bit here just means that we don't want to have the full path in our output. That's no, I wanted to go up here. Let's run this example if you're just looking.
It's just on my system, it's just Python.
Sorry?
It's just Python on my system. It's Python 3, but you don't put 3. Oh.
So if you can, if you're looking at the output, so you see that the first function has taken a very short time to run, and then the second function takes a bit longer. And then you get this kind of output. So you see what time each of these will take. It has the two functions, function 1 and function 2 on here, and it will also tell you what all the inbuilt functions are doing. And then if you scroll down a bit further here, that's our other function, and you can see in here, so that basically because one of the functions has been very, very quick and the other one, which is called by that function, has been a bit slower, we're basically getting the same time for both. What you can do now, if you want to do something a bit more interesting, is you can just go in here and maybe increase the time that each of these functions uses and so on. You can do that in the exercise if you want to just add another sleep statement here, and then you can see how the functions are sorted, so according to the time they are taken. So if I would now want to know a bit more in detail, okay, I now know what my functions are, where my functions are, what my functions are spending in terms of time, but I'm more interested in, okay, where in my function is this actually happening? I can also look at where in each functions, or in a line type of way, the time is spent. So I'm going to the line profiler example, and this is exactly the same thing. It does exactly the same as the function before. You will need to pip install the line profiler for this, and then you have a bit more of an verbose stuff happening down here. So you will need to create your line profiler, and then you create the wrapper around the function you're calling. And if you're having more than one function, you will need to add each additional function apart from the function you're calling to your profiler before you can then run your wrapper and look at the statistics. And I'm going to show this to you as well. So you say it's Python.
My fault.
Did you activate the bug environment in that environment? Okay. So yeah, we're doing exactly the same thing, and the nice thing about the line profiler is that it tells you basically line by line what the time is spent in. And you can see, okay, actually all of the time that we're measuring is spent in the sleeping function here. And that is also reflected by the fact that all of the time in the other function is spent by calling the first function. So this can be just very useful if you're trying to figure out where in your code the bottleneck lies. So I think the best thing to do with these kind of things is really to try it out at your own code and see how it's useful for you and how you can adapt it. And then there is lots and lots of online documentation, and then you can basically dig in all the options that you have and find out how to adapt these tools to your needs. Memory profiling. So you might have an issue in your code that your code is failing, and you're quite sure that there's a memory bug somewhere. And one of the tools that you might have heard about is Wallgrind, however people think it's pronounced actually, and you might have seen these nice little pictures around there. I really like them. I've still not found out why St. George is depicted with this. I think it's to do with killing the dragon, killing the bugs, or however. And so on the website it just says because Wallgrind was invented in England. I don't know, but it's a very powerful toolbox. It's not a tool. It's actually a whole range of tools that you can use for various things that you might want to do or might want to find out, and various bugs that you might want to detect in your code. when you say a wall grind, most people will first of all think about the memcheck tool. So memcheck is actually the default. So if you run wall grind without giving an explicit tool, it will always run the memcheck. And I won't show an example. I think you will show the example in a moment. But if you want to use wall grind, you just have to basically compile this with a debug flag and then run it with, basically giving it the executable of your program with the arguments, and either you tell it which tool you want to use, or if you want to run memcheck, you don't need to do that. You might want to check for memory leaks. And then again, just be aware that this will add quite a lot of overhead to your program, so it will make things much slower. You're showing the example.
Thank you. So, yeah, you might be like, oh, I don't want to slow down my code 8 or 10 times to run for memory errors, because especially if your code takes a long time to run already. So you might have a version of your code, your weather code, climate code, and maybe it takes an hour to hit some bug, some memory issue. If you use Valgrind, the overhead is about, you can see from their documentation, it's not, I'm not like throwing shade at Valgrind, it's about 8 to 12 times slower to run the code. And so, like I said, if it takes an hour to run, that probably won't be feasible. And this is where memory sanitizers come in. So they work in a fundamentally different way. It's done at the compile level. So you compile with the debug flag just so you get nicer output. I'll show you the difference later. But the key is we now use fsanitize equals address. These are called sanitizers. There are many of them. It's not just, so we're going to look at address today. I'll show you how to see the others, but there are some that help you find race conditions if you've got threading, and there's many other tools that I can't even remember. But the key one today is going to be address, and this is much faster than Valgrind. We're talking it adds maybe like 5% overhead, and it's much quicker to run. It's not as fully powerful, and like Valgrind is a huge tool with lots of different. It's multifaceted and lots of different ways to use it. The sanitizer is just to focus on memory. Yes. Yeah, so the question is, they've used in the past Valgrind to catch seg faults. Does this catch seg faults? Yes. So if the seg fault relates to a memory bug, then it will catch it. So sanitizers were initially brought in through Clang, as far as I'm aware, so the LLVM project, and the support was initially added for C and C++. It's now been extended to Fortran. And the sanitizers have been ported to the GNU compilers, so not just needing the LLVM ones. But I've noticed the Fortran support isn't as good as the C++. And so I think it does struggle to detect memory leaks, but it will detect memory invalid writes. So if you try to write to memory that is out of out of bounds, or that you don't have permission to, traditionally speaking, or that you haven't, if it's out of the bounds of the array that you're trying to write to, that will generate an invalid write or an invalid read, and then that will trigger the sanitizer. But there are some differences, and then sometimes you do have to switch to Valgrind. But I'd say try sanitizers first. It's much quicker, and it will help you spot memory bugs. Thank you for that question. So we're going to do a couple of demos, as I said. The demos are available in the slides, and for anyone who's found our profiling workshop GitHub, just to let you know, the slides can be found here. And if you click that, obviously it opens the slides, and it's a kind of circular dependency, so you can get whichever one you can't find. So let's take a look at the memory demo. Just to point out again, I'm not expecting anyone to read this. Can I collapse that? Yes. Again, each of the sample folders, so the Python one, the Scorpy one, the memory leaks folder, we have a README that explains how to build the examples, how to go through them, and what you should expect as output. So if this is too quick for you, please go back, do it in your own time, and go through this documentation. So we're going to go back to the memory demo. And this time I've tried to cater more to the diverse audience. These tools are predominantly designed for compiled languages, although apparently you can support Python with Valgrind. It doesn't have a compiler, so there's no sanitizer for the Python one. But still, I've written a code in C, and we also have one in Fortran. So I'll show you the C one. This is taken from Valgrind's website. It's an example case that you can run. I've commented the code, or there's some comments in the code to describe some of the problems, and will indeed identify and validate that. And similarly, if I go to the memory F90, you'll see that there's also similar prompts. So these things here which say problem and then a possible solution, problem and a possible solution. Okay, so they're paired with the numbering. But let's run one and see what happens. So I'm just going to split my screen so I can show the code and the output at the same time. And this is using tmux. I'm not expecting anyone to know what tmux is, but I can just have two windows simultaneously. And I'm wondering if it's best to do it horizontal or vertical. Let's take a look at the C one first. And we're going to try running Valgrind first. I'm not going to have enough screen real estate, I appreciate, so let me minimize that for now. But if I go to the README, I'm going to take a look at compiling. This is the C one. So I'm just building with GCC -G to get debug symbols, and then the rest of it's standard compilation. That gives me something called test C. And if I run it with Valgrind, so I'm not going to put any options initially, and then I'll explain which options we're going to add. So I'm just going to run Valgrind. So Marion already mentioned the default will be to run memcheck. We're going to get some kind of, I find it quite verbose output, considering this is like 5 lines of code. But it tells us at the end, you can rerun with leak check full for full information. So I'm going to add that now. Oops, I can't copy paste. Copy paste. Okay. So now I'm going to rerun it and clear the screen, and I'm going to rerun it with the full information. And there's a couple of things I want to highlight. The first is it tells us we have an invalid write of size 4, and then it tells us the line of code. So if I get the code back, and then let's go to the invalid. Okay. Let me open. Oh, that's because it's in my terminal. I was like, I can't use Vim. So invalid write of size 4, and then it tells us it's on line 6 and in line 13. And if I go to line 6, I can see we've allocated an array of size 10, and then we're trying to access the 11th, i.e. in the indices start from 0 in C and C++, and we're trying to access the 11th element of memory, and that is invalid. Well, we're actually trying to write to it, so we're setting it equal to 0, and so we get an invalid write 4 bytes in this location. Very good. If you didn't build with -G, you're just going to have some cryptic stuff here, and you're not going to have the nice line numbers. So that's what happens if you don't compile with the -G. It will still run, but the information is not so helpful. If we scroll down, there's another memory problem, and we can see that with heap summary. In use at exit, we had 40 bytes in one block, and it's going to try and tell us that some memory's definitely been lost, record 1 of 1, and it was allocated. It can't tell you where it was not deallocated, but it can tell you where it was allocated. And so it says alloc line 5. We go to line 5. That's this line where we allocated the array. Okay. Obviously, because we didn't deallocate it, it can't tell us where that was. And so what I'm now going to do is I'm going to take the fixes. So I'm going to comment this line out, or I can just change it to 9. So we set the 10th element to 0. And I'm going to be a good C programmer, and I'm going to remember to free the memory. Okay. So now if I save this, I'll go down to the bottom. I'm going to recompile. And now I'm going to run Valgrind with the full leak test, etc. Let's make this full screen. I'm going to run that. And now I will see everything is A-OK. There were no invalid writes. There's no memory that's not been freed. no leaks are possible, magic, happy days. Okay, so I'd encourage you to play around with this. It's a very small example, but it helps build that intuition, build that understanding of what Valgrind output actually means. So you can add some deliberate errors, change the things, see what happens. Now I want to show you the sanitizer. Now, speed-wise, you're not going to see a difference. These codes are so small, but you just have to either read the documentation of Valgrind or take my word, it is slow. Okay? But now we're going to see the alternative approach and what that looks like, and some kind of pros and cons. So we're going to take exactly the same code. I'm going to reset it. So it's exactly the same code, and I'm going to show you the command. So now we're going to, I'll explain each bit of this in a second. So as before, we have GCC minus G. That gives us the debug symbols, so we get the helpful line information. We're using the sanitizer, F, oh, this is weird highlighting, come on. Okay, never mind. It's not going to let me win. But we've got this minus F sanitize equals address. That's the thing that actually helps us with the memory sanitizing. And then we build it as normal. So the only difference between this and the Valgrind example is this new flag minus F sanitize equals address. So let's compile the code with this. And now we're going to run it. Now the key thing is last time we had to prefix with Valgrind. But this is a little bit like the instrumented binary that we saw earlier with the Scorpy. It's like hooks have been added to the code, and it will now kind of check these memories without the need to run any additional programs. So you run it exactly as you would run the normal binary, no extra commands, you just run it. And now we're going to get an output, which is going to tell us, which we've got a write of size 4, this thing, so an invalid write, and it's going to give us the line number, so line 6. Okay, so it's exactly the same place that we saw last time. Now, the thing with sanitizers, unlike Valgrind, which will run your whole program and then give you an output at the end, the sanitizer stops at the first memory bug, which is very useful because then you can fix that memory bug and then move on to the others. Whereas in theory, like Valgrind, you can be like, oh, I fixed the main one that solves my problem, and now it runs and finishes to the end. Whereas with the sanitizer, you need to fix them all to get to the end. And I would encourage you to fix them all, because they will, you'll thank yourself or you'll hate yourself. So we're going to change the first one. I'm going to fix that, but not, I'm not freeing the memory. So now I'm going to go back, I fixed one problem. I'm now going to recompile, and I'm going to run my code again. And it's detected a memory leak because we didn't free the memory. It tells you it's online. Well, again, it can't tell you where you didn't free it. No surprise. But it can tell you where you allocated it, and that was on line 5. So if we go back to the code, go back to the code, go to line 5. Indeed, we did allocate some memory here. Where do I think I should deallocate it? Well, I don't need it anymore, so I'm going to free it at the end of this statement. And I'm going to save. And now I'm going to go back to the drawing board, recompile, and run my code. Perfect. Thank you. Right, okay, so that brings us to the end of the worked example. There are examples for Fortran. It's exactly the same. If you're more comfortable with Fortran, get into those demos, play around with it, deallocate memory, allocate it, see what happens. Try and access memory outside of the bounds. Everything you need is in this description. So the question was, are there cases where you would like to skip certain kinds of memory errors? I'm going to say no, because so there are many running codes with no doubt in my mind today that decisions have been made on codes with memory bugs, 100%. You can never have bug-free code, right? If you've been lucky enough to be given the gift of knowledge that you do have a memory bug, fix it, because you can tell me, oh yeah, but my code runs and I get good results. You're probably overwriting a part of memory that doesn't matter now. What happens is when your code gets bigger and your arrays get bigger, eventually those invalid writes are more and more likely to occur on a part of memory that you really need. You've got some array that's got maybe all your state variables in, and then you make some temporary array, you go out of bounds, and it's overridden your first level of your atmosphere with completely garbage data. You then go write a paper about it, and base a 6 months research on this interesting anomaly you found over the tropics, and it's just a memory bug. You'll never get a compiler warning, you won't get a runtime warning, it's just going to silently corrupt your data in your code, and it's very, very hard to spot. So if you're lucky and you write bad code, you get a seg fault. If you're not lucky, it runs and it gives you data and you write papers and you'll never know. So I'd encourage you to fix any message you find. But that's not to say that Valgrind can still have very verbose output. So specifically for the Valgrind tool, it may have suggestions of things that maybe like warnings that aren't errors. That can be left to your judgment. But yeah, it's best to try and fix as much as you can. Are there any other questions? So that and then immediately look down. Any questions? No? Okay, so that brings us to the end. Thank you so much for listening. And all the example codes, they're all on the GitHub. It's all linked there. Slides are available from the GitHub. Go to Cambridge-ICCS Profiling Workshop. You can find everything. And now we want to give you as much time as possible. We've got till 3:30, about 50 minutes. Have a play. Try and install these things. If anyone wants to use Scorpy, I'll be milling around. I can help you try and install it, help you try and add it to your build system, your workflow. If you want to mess around with the Python stuff. If you want to do the memory profiling, you can use our examples, you can use your own code, but I'd encourage you to try and use your own code where possible. So this time's for you, 50 minutes, whatever you'd like to do. Thank you.